So my talk today is on data-driven optimization, and I'm sorry. There we go. Analytics, as you probably know, is the tool that we use to unlock the value and the potential of big data. And analytics roughly can be broken down into three subcategories: descriptive analytics, predictive analytics, and prescriptive analytics. And most of what I do in terms of my research falls in here. I basically study optimization problems of all sorts of different kinds. And an optimization problem in general kind of looks like this. You tend to minimize or maximize some function. You have some constraints, whether they're inequality constraints or equality constraints. And then you have your decision variables that, of course, that your computer is going to try and find the best solution, that is the best value of x that satisfies these constraints and also lies in some feasible domain x, which I've illustrated by this set x here. And so typical sets for the x could be, real numbers in Rn or integers. There's many applications for optimization. In the business context, for example, we could be talking about optimizing marketing campaigns, doing portfolio optimization, generating schedules or timetables, optimizing supply chains, and so forth. The process, regardless of application, tends to take the following form. You start with defining a problem, and then you abstract that problem to create what's called a formulation of that problem. And so, although you may be clear on what the actual problem is that you want to solve, it often happens that there could be more than one formulation to solve that problem. And these formulations, although logically equivalent, could have very different characteristics in terms of their efficiency for solving the problem. And then we're going to solve one or more instances of that problem using what's known as a solver. So some common solvers are Cplex, Gurobi, or Nitro, for example. These are essentially softwares that operate on various different classes of optimization problems. And then once you solve the problem, you can communicate the results to various stakeholders or automate the process if you were implementing this, for example. And so I've illustrated this process as kind of like a linear process here, right, where you follow these steps in order, but actually it's not really. You kind of go back and forth and adjust the problem and the formulation and even some other properties, for example, of maybe what you think are relevant instances as you learn things as you solve the problems, right? In any case, depending on the particular application that you're working with, there may be one or more computational difficulties when you're solving an optimization problem. For example, you might have too many constraints, maybe very hard to deal with this number of constraints, or you could have, say, a ridiculously large number of variables. And so a lot of what I study is large-scale optimization, which basically means I'm trying to find structure in optimization problems so I can break apart or decompose these problems into more manageable pieces and or approximate the formulation of the problem with, for example, a simpler formulation, so I get a solution that is fairly close to optimal for the original problem, even though I'm not able to actually solve that original problem. And so today I'm going to give you two examples to illustrate what I'm talking about here. The first deals with planning of online advertising, and then the second talks about locating trauma centers at the nation scale. Okay? So with regards to planning online advertising, whether you're planning ads for web pages or for video game consoles or for digital television, the setup, or in the abstract form, is roughly the same. It basically involves trying to match viewers on this side here with advertisers over here, right? So which advertisers get to show their ads to which viewers. But that's, of course, a simple description of the problem. As you can probably guess, there are different viewer types, and each advertiser has a preference for different viewer types, which are illustrated by these links here. So we call these targeting requirements. And each advertiser also has a different impression goal, or a desire for a number of exposures from these viewers. Right? And so the challenge is to solve an optimization problem that allocates a number of exposures or impressions to each advertiser from each type of viewer. And we have some forecasts available to us that tell us roughly how many viewers of each type that we're going to have. Right? And so historical data can be used to figure out what a good estimate is for the number of viewers of each type. There's only one problem, of course, and that is that there are many dimensions that advertisers can specify their targeting requirements. So advertisers can say, well, we want to show our ad only to specific genders, people of certain ages, in certain geographic locations, at certain times of the day, and perhaps to people who like specific sports. Okay, the number of dimensions here is essentially endless in terms of what you could possibly model. And so when you think of this optimization problem, which is essentially a planning problem, you have to simultaneously deal with the requirements from all of these advertisers, where each advertiser is saying, I want these viewers, and another advertiser says, I want these viewers, and of course there's some overlap. And then another third advertiser says, I want these viewers, and now there's pockets of overlap here. And as the number of advertisers increases, the number of unique pockets of viewers grows exponentially. And we call that combinatorial explosion. Okay, so the challenge is, of course, how are we going to, one, represent such a large-scale problem here where you can have billions of viewer types on the left-hand side, and if you were even going to solve this large-scale problem, then another issue is how do you forecast the number of individuals that are going to possibly arrive of each type when each bucket of individuals is extremely small. Okay? And so the answer is you aggregate the problem in an efficient way, right? And we solve this aggregate problem, and if you do this in a good way, you're able to get a solution that is in fact very close to the optimal solution for the true disaggregate problem without ever solving this true disaggregate problem. Okay? The key here, of course, is not to choose manually how to aggregate your viewers into buckets, but rather to allow the optimization to segment the viewers. Okay? And so we end up with an iterative process where you solve the problem, you learn something about the solution, you revise your instance, and then you repeat. And so the data requirements, they change at each iteration, which means instead of having a process where you first construct estimates of your model parameters, and in other words do forecasting and data mining, and then solve an optimization model, what we really want to do and focus on in data-driven optimization is we start with some coarse approximations for the model parameters, solve an optimization model, learn and revise the model, resample the data to improve forecasts, and then iterate until we come up with something that we feel comfortable with. Right? And in the context of online advertising, you can often get to within 1% of optimality with less than 100 judiciously chosen audience segments. And this is really great, right? But the price you pay, of course, is you have to iterate through this 15 or 20 times or so. Okay, so that's one paper. The other paper that I'd like to share with you, a couple of insights here. I did some work with some co-authors. We were trying to improve the trauma care system in South Korea. And in case you didn't know, South Korea is a country that has approximately 50 million people, and it has an area about the size of Indiana. On an annual basis, there are almost 200,000 trauma cases, and there is a significant gap with respect to the United States in terms of their the criteria that they use to measure whether or not patients could possibly be saved if the trauma care system was improved. And so we looked at this problem, and we wanted to try and figure out if we were able to select a subset of candidate trauma center locations and simultaneously select a subset of helicopter locations, then how could we end up with a solution that is near optimal and could do better than perhaps the existing solution or system that they have right now? Okay. So this again becomes a large-scale optimization problem, and when solving this problem, this is the method that we use to solve the problem here, and it's a sophisticated method that solves for both the trauma centers and the helicopters simultaneously. And we have two benchmarks here, right? The decoupled method and the no congestion method. I won't give you details about what these methods do right now, but what I want you to realize is that the solutions of these three methods visually don't look a whole lot different. But if you measure the quality of these solutions, they are actually very different. And so you cannot tell by looking at the solution how good it actually is. Here is an illustration of the quality of the solutions that we get from these three methods. Our integrated method is here. Here are our two benchmarks here. And the main thing to note here is the decoupled method plans the trauma centers first and the helicopters after, and uses more sophisticated models for the trauma centers, or sorry, more accurate models for the trauma centers in isolation and the helicopters in isolation than the integrated model that combines the solution of the trauma centers and helicopters into one step. But what we find is that integrating the model, putting things together in one step, actually has more value than having a more precise model where you break these two solution steps apart. Okay, and so the takeaway here is if you realize that you can actually do well or with an approximate model that simultaneously solves for two things at the same time, well then that also relaxes some of your data requirements, because once you are okay with having an approximate model, that reduces the number of parameters that you need to fit from your data set. Okay, so the takeaway is that there's many big challenges, and I would sum it up as what we want to try and do is to predict and optimize instead of predicting and then optimizing. Okay, so thank you very much.
Thank you, John. So for the last few minutes, we'll open it up to questions for any of the 6 speakers in the last session. So please fire away with your questions about our diverse topics. Yes?
My question is for Daniel. Hi, my question is using the camera, using the phone camera to detect space particles is so interesting. My question is the information you are looking for about the particles reside in the photos, or you have to do extra processing step to detect the particles?
Right, so when a particle hits the CMOS sensor, it deposits a little blob of energy. So what we're looking for, for example, if your camera is covered so the picture is otherwise black, it's just a little hit, a little white spot. So on the phone, we do a little bit of processing. Also, we're not interested in uploading full images, and for privacy reasons, we don't want to turn people's video cameras on in their bedroom at night and upload video to the cloud. So we just scan the camera very rapidly and look for hot pixels. And the only thing we're measuring is, did your phone see a particle or not? And then if you have a bunch of phones nearby, then you could say, oh, this person's phone saw a particle, this person's phone saw a particle, that person's phone saw a particle, and it's the coincidence of hits in many phones at once that tells you that you saw something from space. But this application of it is just one idea. There's one open question in physics about cosmic rays, and we can use smartphones to answer that. The same network potentially could be used to answer lots of other questions. For example, we demonstrate that the phone is sensitive to the presence of ionizing radiation. That means that it's also effectively a dosimeter. And we've tested this in the lab. You bring a radium source, for example, close to the phone, then the app lights up. And if you move it away, the app quiets down. So essentially, the app can serve as a cheap dosimeter. You can turn it on, and at night, if there's a radon leak in your home, it can tell you. The other interesting aspect of that is, if you have an internet of these things around the world, you can build a live radiation map of the world, which doesn't currently exist, to my knowledge. I mean, maybe the NSA has one or something, but we don't have access to one. And from a public health point of view, it might be very interesting next time there's a nuclear disaster somewhere to say, is the plume coming to the west coast of the United States? Should I head up in the mountains? Does that make my life worse or better? I think that could be pretty interesting.
So do you have an app for this kind of detector?
Yeah, we have the app, and the app works, and
It works both for...
it's exactly the same technology. If you're seeing particles, they could be from space, or they could be from radon, or they could be from Putin's latest test. It's the same kind of particles. Yeah.
So I have a feeling we could let Daniel speak all evening and it'd be quite fascinating, but in the, to be fair, let's see if there's any questions for some of the other speakers as well. Or maybe we'll have to go back to Daniel. Let's see, well, you had asked some questions beforehand. Let's see if there's anybody else who has some questions. Very quiet Friday afternoon audience here. People are itching to get to the, okay, well, go ahead.
Sorry, I have a lot of questions. So for Jim and perhaps for John, the fire prediction, did that take into account data in terms of its geographical, the influence of the 3D dimension of where this data is coming from, and perhaps flows and things of that nature? And then this, kind of ties to the optimization aspect that was discussed right now, where you combine data from different sources and get more information.
So, it's short answer is no, it really didn't. I think there's a lot to be done to optimize the area of influence for these different particular zones in the Amazon, or just globally. So I think that's a really important next step, is to try to do some kind of a cluster analysis or some kind of a search to find out the areas of influence that don't correspond to the existing climate indice regions that are well established, and to then try to see if we can improve the predictability of the early warning system. So good question. Thank you.
Question at the back. I think this will be the last question, I think. And, I think people are keen to get to the reception.
Thank you for the excellent data science initiative meeting. I have a very generic question to all the audience. What are the needed infrastructure support for the big data science? Because how to move the data, what kind of support do you need? Because we are more from the technical side, and science is great, but what kind of technology support you need, and how we can work with you, and also how to visualize the big data. And those are two questions I'd like to get some reading from the speaker and see how we can work with you.
So GP, since I was a speaker, this is not probably the answer you wanted, but I would say more people. And so I think we can throw as much hardware as we want, but I think it's people, it's the key thing. And, sorry, that's a little bit of a cheat of an answer. Anyway, on to the other speakers. Anybody want to answer GP's question? Infrastructure, resources, this is your chance. Director of CalIT2 asking, what do you want?
I'll take my chance. This is some discussion we were having So this is some questions that we were discussing with the OIT people here for the HPC computer. So for example, in my case, sorry, and I'm making my point. You have seen that we can have a lot of data potentially available, but then we need an enormous amount of storage space. We need an enormous amount of storage, which is just transient, because when you do calculations in both brain imaging and genetics data combined, then you explode your data set in a kind of a gigantic hundred of terabytes storage system. Okay, and then you need a super fast CPUs, but you need also a lot of RAM memory. So we have experimentally used machines that have up to 2 terabytes of RAM memory for a single unit. And we are now working with machines that have 412 gigabytes of RAM memory per unit. And then we have 64 cores and blah, blah. But what I'm saying, we need a lot of technology and a lot of infrastructure just to have this kind of data set available. And I don't know if I have answered your question, or I give you an idea on what we really need. And another important point is what you have highlighted, which is how do we visualize the results? How do we visualize the systems? So that is, I think, an unmet need in my field at least, because we have several different options to visualize the results, but making an integration of different results from different domains into a unified visualization system is still a big challenge.
All right, thanks. I'd like to thank all 6 speakers in that second session for not only presenting sort of fascinating cross-section of different applications, but also for staying on time. That was great. 10 minutes each, fantastic. So a round of applause for... So I'm just going to, just closing remarks, which I promise won't go over 2 minutes. It seems like a long time ago that I started out speaking this afternoon. We've had 11 talks, if you count mine. Thank you for sitting through all of that. I think it's striking the diversity of sort of intellectual ideas and applications that are involved in data science, and that was part of the goal, to bring together people from different parts of campus. But nonetheless, there are common themes. I think you saw ideas from statistics, from linear algebra, from optimization cropping up all over the place. You saw people doing very creative things by combining different types of data, climate, genomics, brain imaging, and so forth. And you also saw themes such as predictive modeling showing up. How do you test these models? You simulate, you predict, and that's very, very important. I think the challenges that we heard about, there's infrastructure challenges, clearly, computation, storage, they don't go away. Maybe a little more subtle, a few people mentioned, including Mark and some others, about understanding the information that's coming out of these models. We can go from data to models, but even the models themselves are so complicated now that getting to actual useful knowledge is not that easy. And then Jeff gave a really interesting talk on the sort of dark side of big data that I think is creeping into a lot of aspects of our work. As the director of the Data Science Initiative, my sort of advice or charge to you is to go forth and interact. With that, we have the reception, but I'm actually serious about it, particularly grad students. Despite what your advisor says, get out of the lab, go across campus, talk to some of these other people who are doing things in earth system sciences, in climate, in biology, in business. The goal of the Data Science Initiative is to try to create some of these cross-links between departments that don't already exist. So I'm hoping this afternoon might have helped get some of that started. Very finally, thanks to a few people, Susan, Diana, Andrea, Kevin, for keeping time. They did a great job behind the scenes here. So we're ready to please go to the reception and enjoy. It'll be food and drinks are outside. Thank you.